Hello everyone, welcome you all at Lokesh Sir Unlimited Study Zone. So in our electromagnetic induction classes, we're starting our today's topic, and topic of the day is motional electromagnetic force. Student, yesterday we have talked about the flux, and as Faraday's law, the amount of EMF, induced EMF, is directly proportional to rate of change of flux, right? And after Lenz's rule, the final we have derived, the relation is E is equals to minus d phi by dt. As I told you, there's a rate of change of flux, and the amount of flux is given by NBA cos theta. Okay, so there may be change in magnetic field, change in area, and change in angle. Okay, change in these quantity will results the production of induced EMF. Okay, so by one cases, we will see how these quantities are changing and produce EMF. Yes, first is motional electromotive force. Motional electromotive force. So the concept behind this is by changing the area. Okay, means there is a coil. Yes or what? Okay. So today our concern is to find the electromagnetic forces because of change in area. Remaining all the things n, b, a, and theta will be constant. Clear? So this category of generation of electromotive force is called motional electromotive forces. Yes, figure shows a rectangular conducting loop PQRS. So you have to take a rectangular loop PQRS. So this is a like this shaped loop there. Okay, with a movable arm. This is the movable arm. Okay, you can slide this arm over this U-shaped conductor. Okay, yes. So PQRS. Previously it is A and B. Yes. So PQRS is the area of the loop. Okay, PQRS is the area of the loop, and you can slide this branch over this length AS and BR. Okay. So figure shows a rectangular conducting loop PQRS in the plane of paper. The conductor PQ is free to move without any loss of energy due to friction, etc. It means there is no loss of energy. It is free to move. The magnetic field is perpendicular inward to the plane. Yes, this is important line. The magnetic field is perpendicular inward the plane. Right, beta? Now you see the direction of the plane, magnetic field is going inward. So here theta is equals to theta may be considered as 0 degree, right? Because the normal of the plane is also can be considered as inside, and magnetic field is penetrating inside in the same direction. So theta is equals to 0 degree. Clear? Yes. So magnetic field is perpendicular inward. The magnetic field is perpendicular to the plane of the paper and directed inward. Let the conductor PQ move towards the left with a velocity v. Now, so this the conductor, we can move this conductor with a velocity v. Now tell me, when you slide this conductor towards here, does therein is change of area of the loop? Yes or no? If you slide the conductor towards this side, there is a change in area of the loop. Yes or no? Area of the loop is decreasing. Clear or not clear? So let the conductor PQ is moved towards the left by a velocity v. Okay, you have a particular velocity, suppose v. By a constant velocity v, you are moving this conductor branch PQ. Okay. due to which the area enclosed by the loop PQRS will be decreases, because previously PQ will be here, but after moving up to here, the loop will result a new area, that is a new decreased area, right? Therefore, amount of magnetic flux linked with the loop also decreases, because the value of phi is equals to NBA exactly. So if the area decreases, then the amount of flux is also decreases. This will result the change in flux with respect to time. Right or wrong? Yes. So flux link with the loop decreases and the EMF is induced in the loop according to Faraday's law. Right? If at any time the length of the RQ is equals to X and PQ is equals to L. Yes. See, at some instant, if this branch PQ is at position, this one position. Yes. So if at any time your length of the conductor, effective length of the conductor is equal to X, right? So at any time the length RQ equals to X and breadth PQ, you can suppose PQ is the fixed length considered as L. Okay, so only X will be changed, L will remain constant, because movable arm is changing the X, right? So the magnetic flux linked with the loop PQRS. Okay, so at any instant of time, like the length of the loop is equals to X and breadth equals to L, then that time amount of flux equals to what? Phi is equals to NBA cos theta. Agree, beta? Yeah, phi equals to N. As there is only one loop, so in the place of N there is one. B means magnetic field B given. Area is equals to length into breadth, so you can take L into X. Clear or not? We have taken here capital L, so going with capital L and X. Cos theta, as theta is equals to 0 degrees, so cos 0 equals to 1. So all total flux equals to BLX, right beta? So phi is equals to BLX. If at any time the length of the loop RQ equals to X and breadth PQ equals to L, then the magnetic flux linked with the PQRS loop equal to BLX. Clear? Now, what is Faraday's law? Faraday's law, okay, by now the induced EMF, now then the induced EMF of the loop is given by. So, according to the definition of induced EMF, we know E is equals to minus of d phi by dt. Right or wrong? So, E is equals to negative of d by dt, and the value of phi is equals to B into L is the length of conductor and X. Clear or not clear? So E is equals to minus of B is constant value, so take it outside the differentiation. L having the constant value, only there will be dx by dt. Clear? So dx by dt. Now E is equals to minus of B, L, and V. Okay? Yes, negative sign showing here that the produced EMF will oppose the change of area. Clear? Because it is produced because of changing in area. Clear? So if you're talking about the magnitude of E, so this is equals to E is equals to BLV. This is called motional EMF. Right? Okay. So this is called motional EMF. So E is equals to BLV. Amount wise E is equals to minus, BLV. Here E is called the motional electromotive force. Now, if I want to figure out, if I want to calculate the amount of current flowing in this loop, then what will be the current of flowing in this loop? So, if R is the resistance of the loop at given instant, okay, the induced current I at that instant can be given by the normal formula I is equals to voltage upon resistance. So, in the place of voltage here, EMF is working there, and the amount of EMF equals to BLV upon R. Clear, beta? So amount of current is equals to BLV by R. Clear? The direction of induced current in the direction of induced current is given by the Fleming right hand rule or Lenz's law. Clear? So you can calculate the direction of current using Fleming right hand rule. Let us see here the direction of induced current. Okay, we can calculate here. Yes, take out your right hand. Okay, now take out your right hand and stretch all your fingers like force finger means your thumb, index finger, and middle finger perpendicular to each other. Now, magnetic field is going inside. Okay, first keep your finger, index finger, over the line PQ as it is moving. Okay, so keep your index finger up to on the limb PQ. Now, point your thumb toward the velocity because you displacing your limb this side, left side. So this is the direction of force. Okay, you can observe your middle finger will pointing towards downward. Agree? So okay, so the direction of the magnetic field will, sorry, direction of the induced current is downward. Clear or not clear? So current will be go here anti-clockwise. Clear, cannot clear? Current will be move here anti-clockwise, right? No, no, sorry, it is clockwise. It is going downward, then here. That is clockwise, yes. If it is here, here it is 3. So 12 to 3 is clockwise, right? So current will be clockwise. So this is the derivation for motional EMF and amount of current produced. I equals to E upon R, that is equals to BLV by R. The direction of the induced current is given by the Fleming right hand rule or by Lenge's rule. Clear? Yes. Now, next, so this is a numerical related to this one. Now, if you want to calculate the force on the wire, which wire? We are talking about this wire, okay? This, this one, force. Why force is working? Because we know whenever there is a current carrying conductor placed in a uniform magnetic field, okay, a force will exert by the magnetic field on this conductor, and this force is given by F equals to ILB sine theta. Clear or not? Yes. So this is called Bill sine theta. F is equals to BIL sine theta. Bill sine theta. B means magnetic field, I means current, and L means length of the conductor. Okay. So this is the force. We have derived this one force in chapter number 4, magnetic effect of current. Okay. From there it has been taken. So force on the wire, external force acting on the wire equals to F equals to BIL sine 90. Why? Because the angle between current and magnetic field here is equals to 90 degree. Clear or not clear? Yes. The vector form of the force F is equals to I inside the bracket L cross B. So you have to take the direction of length vector and magnetic field vector. So here the length vector is on y-axis and magnetic field is perpendicular inward. So the angle between L and B is equals to 90 degrees. So this will be equal to BIL sine 90. Now the amount of current I is equals to BLV upon R. Yes, because as equals to E by R, so it is equals to BLV by R. Or we have just proved this amount of current I is equals to BLV by R. Right? We have seen the current amount of current equals to BLV by R. Where? Here. This is BLV by R. Okay. So multiplied by L. So formula equals to B square L square V upon R. This is force on the conductor. Clear? Now next topic, induced EMF due to rotation of rod in a magnetic field. You see here, this is also the case for changing area, but here in the sense of theta, area will change. So consider there is a metallic rod of length L. Initially you have a rod of length L, okay, is placed in a uniform magnetic field, that is perpendicularly inward, going perpendicularly inward as shown in figure. Now area covered by the rod for making 2 pi angle. Yes, if the rod will move complete angle 2 pi, this means 360 degree, then the area swept by this rod equals to pi r square. In the place of r square, there will be l square. Agree? So for the 2 pi rotation, the change in area is equals to pi l square. Yes or no? So for unit area of rotation, the area swept is equals to pi l square upon 2 pi. Pi to pi cancel. This is equals to l square upon 2. Okay. For unit rotation. Okay. Now for any angle theta, random angle theta rotation. So 1 to theta, you just multiplied with by theta. So that is equals to L square theta by 2. This is the area swept. Clear? So the area swept equals to L square theta by 2. Right? Now calculate the amount of flux related with the this swept of area for in particular angle theta. Phi is equals to BA cos theta. So theta is equals to here 0 degree as the magnetic field is perpendicularly inward. So phi is equals to B into A only because cos 0 becomes 1. Clear here? Okay, B into A. Now phi is equals to B and A in the terms of theta is equals to L square theta by 2. So B A square theta by 2. Yes. B, no, not is it A square. Sorry, it should be L square. Okay. Because the value of A equals to L square theta by 2. So it is equals to B L square theta by 2. Clear or not? Now, electromagnetic force equals to minus of d phi by dt is equals to minus of d phi by dt. That is equals to minus d by dt. Place the value of phi here. So this is equals to B L square theta by 2. Clear? Now, B is constant, radius L is constant, 2 is constant. So you can take negative of BL square by 2, take out as a constant. Only here it is theta by dt, d theta by dt. And okay. And d theta by dt is the change of angular displacement. And the rate of change of angular displacement, d theta by dt, is called angular velocity omega. Okay. So it becomes electromagnetic EMF, electromagnetic force equals to minus B square, sorry, minus B L square into omega because d theta by dt equals to omega by 2. That is equals to 1 upon 2 minus B L square omega. Okay, minus sign representing here the opposition of the change of flux by electromotive force. Clear? Yes. So this is equals to BL square omega by 2. Yes. Coming to the numerical. Yes, this is the numerical. A metallic rod of 1 meter length. This means first thing L equals to 1 meter is rotated with a frequency of 50 revolution per second with one end hinge at the center and other end is on the circumference of a circular metallic ring of radius 1 meter. About an axis passing through the center and perpendicular to the plane of the ring, a constant uniform magnetic field of 1 Tesla is parallel parallel to the axis is present everywhere. What is the EMF between center and the metallic ring? Okay. So you have to told the yes area of the loop swept. Okay. Yes. See here. Actually, we already have carried out the derivation. E is equals to B L square omega by 2. Yes, we have this one. Okay. E equals to B L square omega by 2. We already have the result. E is equals to B L square omega by 2. Clear or not? Now this is omega. This is in 50 revolution per second. Revolution per second. Omega is given here 50 revolution per second. Clear? But revolution is not the SI unit. The unit of omega is equals to radian per second. Clear, beta? So you have to convert into the radian. So 50 multiplied by 1 revolution equals to 2 pi radian per second. So your omega is equals to 100 pi radian per second. Clear or not clear? Now apply, you can apply the formula. B is equals to equals to BL square omega by 2. So 1 upon 2. The value of B is equals to 1 Tesla. L square is the length, radius equals to 1 meter. So 1 square. And omega is equals to 100, I think. No? Yes, 100 pi. 100 pi. All the things are 1, 1, 1. So answer will be equals to 50 pi. Okay. So yes, check here. This is 50 and this is the value of pi. So answer equals to 157.1 volt. Clear or not clear? Okay. Yes. So this is the one way to get the answer. Another way, radius of the loop. Write all the things. Radius is given. Magnetic field is given. Consider at any instant of time by rotating this loop is making an angle theta. Okay. So in class 10th, we know the area swept is equals to pi r square into theta upon 360 degree. Yes or no? Area of the sector. Have you studied this one in class 10? Pi r square into theta upon 360. But here it is radian. So in the place of 360, there will be 2 pi. Okay. So it is equals to pi r square into theta upon 2 pi. Clear? So E is equals to B. E is equals to what? D phi by dt, right? So d by dt, and then in the place of phi is equals to B A cos theta. Cos theta becomes 1 because field is perpendicular inward. So may I write here 1 directly? B into A into 1. Okay. Okay. So B is the magnetic field that is throughout constant. So d by dt, B will be carried out and B dA by dt. Now what is area? This is equals to pi r square into theta upon 2 pi. Clear? So pi to pi cancel. It will be b r square and 1 upon 2. So half b r square d theta by dt. Okay. D theta by dt is equals to omega. So again this formula become 1 upon 2 b r square omega. Now by the formula in class 11th, omega is equals to 2 pi f. Okay. F is called linear frequency, which is given here 50. Okay. So place here half br square 2 pi f. In the place of f, you can also take nu. So 2 to 2 cancel 2 and 2, and pi nu frequency b and r square, all the terms. So value of pi equals to, yes, what? Nu, nu, nu. Actually, this is 2 pi f, and f is also called 2 pi nu. Okay, f is called nu. Okay, it came by the formula omega is equals to angular velocity is equals to angular displacement upon total time taken. For complete revolution, total angle equals to 2 pi, and this total time is capital T. So this is equals to 2 pi upon T. Now it can be written as 2 pi into 1 by T, and 2 pi 1 upon T, 1 upon time period is called linear frequency nu. Okay. So this is called linear frequency nu. Somewhere it is also called as 2 pi f. Okay. In chemistry, it is known as 2 pi n. So all the terms referring the same meaning. This is called linear frequency. Agree? And this is what? Angular velocity or angular frequency. So place the values here. All equals to 1. Now this is equals to 157.1. Okay. Or otherwise directly, if you have learned this formula, just apply this formula. BL square omega by 2, and the value of omega is equals to in the form of frequency is equals to 2 pi into linear frequency. So linear frequency is given here 50. So omega is equals to 2 pi into 50, right? Becomes 100 pi. We already have done this. Clear, beta? So guys, this is completion of this numerical. Now, Another numerical. A circular copper disk of radius 10 centimeter rotate with a speed of 20 pi radian per second. Yes, this is in radian per second. So this is omega. Okay. About an axis through the center. Same concept. Here the axis is perpendicular to the sheet. About an axis to the center perpendicular to the axis. A uniform magnetic field 0.2 Tesla act perpendicular to the disk. Yes. Same here, the uniform magnetic field is applied perpendicular to the disk. Calculate the potential difference developed between the axis of the disk and the rim. Yes, first you have to find the potential difference. We're using the same formula, half BL square omega. Clear? See here, that is equals to 1 upon 2 half B omega L square. As the radius is R here in the place of L, so we can take R square. Put these value 1 upon 2 half B is equals to this one. Omega is equals to 20 pi. It is given in radian per second. Clear? And R square equals to 1 centimeter. It is, no? Yes, 10 centimeter. So 10 centimeter converted into the meter. So 10 upon 100, that is equals to 10 to the power minus 1 meter. So place here 10 to the power minus 1 meter. This is your answer for the EMF. Clear? Now, if asked about the current, I is equals to EMF upon R. So E by R, that is equals to 0.0629 upon 2. This will be your answer. Clear? Yes, the next numerical, coil of number of turns N, area A is rotated in a constant angular speed omega in a uniform magnetic field B and connected to a resistance R. Deduce the expression for the maximum EMF induced in the coil. Okay, beta? Yes, a coil is there having the number of turns and area A is given the coil of area A. Okay, and moving with a constant velocity omega. You have to find the maximum EMF induced in the coil. Yes, look here. In this way, a coil is moving there. Let initially area vector A of coil make an angle theta with the direction of magnetic field. See here, the coil is moving here. Okay, so a simple flat coil is there. Now, initially your magnetic field is like this. Okay, so where is your area vector? Area vector is just front towards, it is pointing towards your nose. Okay, so a angle equals to, first angle equals to 90 degree. Now slowly when it will move, you check there is angle is decreasing, and if this coil is here at some place, then the area vector will make an angle theta with the magnetic field, right? Yes, the speed of this coil is equals to omega. So let initially the area vector of the coil make an angle theta with the direction of magnetic field. So at some place, if the angle is theta, let the coil rotate by an angle theta with the magnetic field in time t. So the formula for omega, omega is equals to angular displacement upon time t, right? Angular velocity is equals to angular displacement upon time. So theta is equals to omega t. Clear, beta? Theta is equals to omega t, as omega is equal to angular velocity equal to angular displacement upon time. Class 11th formula. So theta is equals to omega t. Now, magnetic flux link with the each term of the rectangular coil. What is the value of phi? Phi is equals to B dot A equals to B A cos theta. Here we have considered the number of term equals to 1, as I am talking about each term. Okay. So B into A cos theta, the value of cos theta is equals to cos omega t. Theta is equals to omega t. So here phi is equals to B into A cos omega t. Now, induced EMF is equals to minus of d phi by dt. Okay. So this is equals to minus of d by dt, and here it is equals to B A cos omega t. So this will be equals to minus of BA and d by dt cos omega t. Omega minus BA, as omega is the coefficient of t, so it will be taken out, and the differentiation of cos omega t equals to minus sine omega t minus and minus sign will be cancelled out and it is equals to BA omega sine omega t. Clear, beta? Yes, this is what, this is induced EMF in the coil. So this is equals to minus BA omega sine omega t. Now minus sign is cancelled, so it is equals to EMF is equals to B, only BA omega sine omega t. This is for 1 ton, induced EMF in 1 ton. Okay. Now for n terms, just multiply it by n. So for total n terms, it will be equal to NAB omega sine omega t. Clear or not? Now, when omega t is equals to 90 degree, the value of sine is maximum. So for maximum EMF, NAB omega and the value of sine omega t must be equal to 1. So the maximum value equals to NAB omega. Yes. So replace here, E becomes E maximum sine omega t. This is the amount of EMF produced. That is equals to E naught sine omega t. Clear ki not clear? E equals to E naught sine omega t, where E naught is the maximum or peak value of the EMF induced in the coil. E naught is given by NAB omega, that is equals to NBA into value of omega equals to 2 pi f. Clear? So first it is completed. The maximum amount induced in the coil will be E naught. Clear? The maximum amount. First, they inquire about the maximum amount. So for the maximum amount of EMF, the value of sine should be equals to 1, as the maximum value of sine equals to 1 here. You know the maximum value of sine theta is equals to 1. Okay, at theta is equals to 90 degree. So there will be maximum amount of EMF equals to E naught equals to NAB omega. Clear? Now they inquire about power dissipated. So by class 10th formula, we know power equals to V square by R. Okay, P equal to V square by R. In the form of V, we have EMF E square by R. So place here value, the maximum power dissipated equal to VRMS square by R. That is equals to ERMS square by R, where R is the resistance. So ERMS equals to how much? In AC circuit, we will learn what is the value of RMS value of any quantity RMS value. The RMS value of any quantity is equals to peak value divided by 2. Better make this one as underline and write it. Any quantity RMS value equals to peak value divided by root 2. Clear? Yes, RMS value of any quantity is equals to peak value of that quantity divided by root 2. So if you're talking about RMS, IRMS, the value of RMS value of current, so it will be the peak value of current divided by root 2. If you're talking about ERMS, that is equals to electromotive force RMS value, that is equals to peak EMF divided by root 2. It is also written as E naught by root 2. Clear? Now VRMS equals to V naught by root 2. Clear? Okay, so place here ERMS square by R. Now ERMS equals to E naught by root 2. We already have the relation about E naught. E naught is equals to NAB omega. Okay, divided by root 2. So place here the value of P is equals to ERMS ka whole square by R. P equals to V square by R, and the RMS value would be taken here. So here in the place of V, there is E square of RMS value divided by R, and ERMS equals to E naught by root 2. Okay. So here E naught by root 2 whole divided by R, and square will be there. So here equals to E naught square upon root 2 square. Root 2 square becomes 2 and multiplied by R. Now place the value of E naught square. E naught is square equals to NAB omega. Yes, check here. It is equals to NAB omega. So NAB omega whole square divided by 2R. So is equals to n square a square b square omega square divided by 2r. This is the value of power dissipated. Okay. Yes. So P is equals to n b square a square omega square upon 2r. This is the amount of power dissipated. Clear? In some given resistor. Okay, so we are ready with the Faraday's experiment number 2. Yesterday we have seen that in the first part of Faraday's experiment, Faraday's has taken a coil and he moves a magnet. Okay, as the magnet is providing magnetic flux, and by keeping this magnet close and far away from the coil, the magnetic flux is changes linked with the coil, and by changing magnetic flux there will be a production of induced EMF, right? Now what do you think if I have taken an current carrying solenoid? A current carrying solenoid is there, okay, and you know current carrying solenoid, if you provide a current carrying solenoid, then definitely it will having some magnetic field, because current carrying solenoid is behaving like a bar magnet. In previous chapter, we have studied that current carrying solenoid having its magnetic field, right? Now, if you keep this loop here, like this is a loop, okay, and you keep this solenoid nearer to the loop, then there will be a change of flux associated with this loop. Yes or no? Yes, so there will be a change of flux associated with the loop. Yes. Figure shows there's a coil or a loop C of few terms of conducting material insulated one another and connected to the galvanometer. Yes. Check here. This is your detecting coil. You can name this coil as detecting coil. Okay. And this one coil is as source coil. Source coil. A major difference is there. Check here. Here it is a battery. Okay. So if battery, the current is flowing through the coil, then there will be a magnetic field. Okay. Current will flow through the coil, then there will be a magnetic field, like magnetic field in this direction. In what way you can calculate the magnetic field? We already have the law. Yes, see the minute threads, minute these lengths, minute threads. Yes. Now curl your fingers in the way of uh, yes, fold your fingers in the way of curl of these rings. Now check your thumb is going. Yeah, I am talking about the right hand. Okay. So in the direction of these rings, you arrange your fingers and your finger is pointing towards left. Okay. So left will give you north pole and this will be south pole. So field will be emerges from here, and after taking a complete turn, they will insert to there, this side. Okay. So this will become north pole and this will become south pole. In this way, the magnetic field will produce from this source coil. Okay. As this coil is a neighboring coil, clear? C dash is the another coil. C dash is another such coil connected to the battery. As steady current through the coil, C dash is produced a uniform field along its axis. Yes, so this coil is spread a uniform magnetic field along the axis. Now, what is happening? When coil C dash is moved towards the coil C. Yes, if this coil C dash, this is source coil, is moved towards the coils C. Now tell me, does there is increase in flux related to the coil? Yes or no? Yes. So there is increase in flux related to the second coil, or you can say test coil, detector coil. So the galvanometer shows a sudden deflection. This indicates that electric current is induced in the coil C. Yes, so there will be a sudden change in galvanometer. Okay, if the galvanometer initially is pointing in this direction, that is a 0. But as you bring this coil nearer to the neighboring coil, your deflection will be there. Second point. When the coil C dash is moved away from the coil C, the galvanometer shows a deflection in the opposite direction. This indicates that the direction of current induced in the coil C will be reversed. Yes, if you bring back this coil opposite direction, then there is a change of galvanometer in the another direction, right? This means the direction of current, induced current, will be reversed. Agree? There is no deflection when there is no relative motion between these two coils. Yes, there is no deflection when there is no relative displacement, relative motion between these two coils, because change of flux will be zero. Initial flux equals to final flux. Clear? The galvanometer deflection, hence induced current, is found to be larger when the coil are moved faster towards away from each other. Yes, when you keep this coil faster, then your EMF will also greater. Okay, means against two things are there. First, EMF is directly proportional to change of flux, and second, EMF is inversely proportional to change in time. If you merge them, you will have the same result. E is proportional to delta phi by dt. In words, you can write EMF produced, EMF induced is directly proportional to rate of change of flux. Here the coil C dash carrying current behaves as a bar magnet. Yes, we know obviously the current carrying solenoid is behaving like a bar magnet. That's why one of the its side become north and another one is become south. All right, clear or not? So this is the experiment number 2. Now moving to the experiment number 3. One more important experiment. Experiment number 3. Yes, this experiment is somewhat different. Check how. This is our current coil. You can say this one as source coil. Okay. First, this coil is open, means no current is there. And we know as the current is flowing, then only the flux will be generated. So when I is equals to 0, okay, at start I equal to 0, so flux equals to 0. Agree? Yes. Now, when you turn this switch on, then the current is risen up in the circuit. Okay, like maximum this battery is 5 volt, can permit a current of 5 ampere. Then definitely from 0 to 5 ampere the current will moving like this. Yes or no? First it would have the value of 0, then slowly it will increasing, and after some few seconds it will have a maximum value of 5 ampere. Agree or not? Yes. So current is continuously changing, and as the current is changing by the Oersted experiment, Oersted increases that amount of current, and as he increases the amount of current, the magnetic field also increases. Yes or no? So continuously, for the less amount of current, there will be a less amount of flux, but for the high amount of current, there will be a high amount of flux will be passing through the loop. Yes or no? Means there is a continuously growing flux that is produced by this main coil, source coil, and the same flux is linked with the neighboring coil. Yes or no? So till the maximum current 5 ampere is established, 5 ampere is an example, not considered as for given all for always. For every type of system, it is just for example. So consider up to 0 to 5 ampere, there will be a change in current. Okay. And change of current will rise the change in flux. And the same flux is linked with this neighboring coil. So what happened? Yes. From the experiment 3, Faraday showed that the relative motion is not absolutely requirement. Okay, till now we are dependent only on the relative motion. That only relative motion can produce the electromotive force. Yes or no? We have seen all the cases in that cases we have performed the relative motion. But now here the current can be induced without relative motion. Yes, this is induction, and here you can produce the current without any relative motion. How? Figure shows two coils C and C dash held stationary. Coil C is connected to the sensitive galvanometer G. This coil C is here connected to the sensitive galvanometer G, and coil C dash is connected to the battery through a key. It is observed that yes, when you switch on means battery key is pressed, galvanometer in the coil shows a momentarily deflection. Yes, this question already has been asked. When you on the switch, then does there any momentarily deflection? Yes, a very small deflection will be there. Till the current is increasing, up to that time the flux will be increasing, and in the this coil change of flux takes place. Yes or no? Now tell me, students, in how many coils there are change of flux takes place? In first coil only, or both for first and second coil? Tell me. There is change of flux because of changing of current. It is obvious. So tell me, in how many coils this change of flux takes place? Only from first or both first and second? First, yes, first is the source coil. So definitely it will produce the changing magnetic flux. Okay. And the same magnetic flux is linked with the second coil. So this coil is also encountered with a changing magnetic flux. Okay. So flux will changes in both the coils. So in first coil, because of changing of its own flux, an EMF is produced. This is called self-induced EMF, right? And this process is called self-induction. Clear or not? Yes. By changing its own flux d phi 1 by dt, the coil will produce an EMF across its terminal, and this is called what? This process is called self-induction, right? Yes. But the flux produced by this coil, the changing flux produced by the source coil, also linked with the some amount of this flux is also linked with the second coil, right? That is also changing in the neighboring coil. So the EMF is also produced here by change of flux d phi 2 by dt, and the EMF produced is called mutually induced EMF, and this process is called mutual induction. Clear or not? Okay. So both type of induction will takes place. One is called self induction, that is in the primary coil, and the another one is mutual induction. Clear or not? So two types of induction will be there. Okay. Yes. See here. So when key K is pressed, the galvanometer in the coil C shows a momentarily deflection indicating the current induced in the coil C. Any problem? As the current is changing. Yes. You tell me, after current is establishing its maximum value, like current is constant now up to 5 ampere. After current establishing its maximum value, tell me, does there is deflection is seen in the galvanometer, or again it comes back to zero? What happened? Tell me, please. I said that when the current reaches its maximum value, okay, 5 ampere, now current becomes constant. So does there any deflection? So first it is change in current. So we have seen the momentarily deflection. Then after when current reaches its maximum value, then any deflection will be seen or not? Tell me. When the current will have its maximum value, okay, like you have applied here, 5-volt battery, current is changes from 0 to 5 ampere. Now current is attained its maximum value 5 ampere. So is still there is any deflection or not? So what? Current is reaches its maximum value. What about flux? Flux will be there. Yes, obviously flux will be there. No. As the current reaches its maximum value, so according to that, flux is also reaches the maximum value. Now flux is there, but flux is have its maximum value, not flux is changing. So flux is not changing, so there will be no induced EMF. Okay, because flux is constant. Understood? Yes. Important is changing of flux, not only flux. Okay. So there is no self-induced EMF and there is no mutually induced EMF when the current is maximum value. Clear or not clear? Yes, see. When the key is pressed continuously, there is no deflection in the galvanometer. Why? Because phi maximum attained because of I maximum. Clear or not? Now, now tell me when you keep this key open. Now, until till now it is was closed, so current is flowing. Now you open this key, okay, upward. Then what happened? Then does there is momentarily deflection in the coil or no? Yes. Why? Think. What happened? When you open the switch, what will happen? No, not on continuously. You have off the key. Okay, it is opened. When you keep the key on continuously, then there will be no flux. Sorry, there is no flux change. So the EMF becomes zero. Now, third case, when you open the key, means switch off. You have off the switch. Then what will happen? Yes. Why? There will be deflection, but why? Not proper answer. You see, when you off the switch, the current before off your switch, it attain its maximum value 5 ampere. Okay. Now, when you off the switch, current is again moving from 5 ampere to its minimum value 0 ampere. Okay. So the amount of flux will be decrease. Like the flux are at highest value at 5 ampere. Now again the flux will decrease. So decreasing flux means changing in flux. Now there will be a opposite direction. Deflection will be in opposite direction. Clear or not? Yes. So what will happen? See here. Yes, when the key is released, then the galvanometer again shown a momentary deflection, but in the opposite direction. So galvanometer deflection increases when an yes, this is completed. Now one more extra thing. The galvanometer deflection increases when an iron rod is inserted to the coil along their axis and the key is pressed release. Okay, same experiment is carried out, but one thing changes there. If you bring a iron rod, then what happened? Then deflection will be increased. Why? Because iron is a soft iron is a ferromagnetic material, and when you keep this iron rod inserted within the coil, the amount of magnetic field will be increases. You know, ferromagnetic material, the magnetic susceptibility is quite high, so the magnetic flux will increase. Okay, so current will also increases. This is an extra point. It may be asked what happened when you insert a iron rod into the coil, okay, along the axis. So the galvanometer deflection increases. Understood each and every point? Clear? Yes. So this is a complete experiment. So Faraday's has performed experiment by either moving the magnet, second by moving the coil, or by changing the current in the source coil. Okay. Okay, students. Now moving to our last topic of this chapter, that is called self-induction. Okay. Self-induction. What do we mean by self-induction? See here in the self-induction, what is going to happen? As we know, by a changing flux, if you change the flux by a coil, then by changing the amount of flux with respect to time, you will have an induced EMF, right? Now, if you have a solenoid, ideal solenoid, okay, is connected with a varying voltage. Let your voltage regulator using in fan, okay, 1, 2, 3, 4, 5. A controller knob is there in your fan, right? You moving, you can move there. So here it is a some battery V, and by this knob you can adjust the amount of voltage. More will be the voltage, more will be the current. So now you can change the amount of current by using this controlling knob. Okay. Now suppose this is time t and this is amount of current. Now you're continuously moving this current. Okay. For 1 second, your current is up to 1 second, 1 ampere. Sorry. For 2 second, your current is varied to 2 ampere. In 3 second, your current is varied up to 3 ampere. And 4 second, your current is varied up to 4 ampere. Right? You know, by the Faraday's, sorry, by the uh, Oersted experiment, amount of flux, magnetic field or magnetic flux link with the coil is depending on the amount of current. Means as you increase the amount of current, the amount of flux also increases. Yes or no? B is proportional to the amount of current. We already read that. B is proportional to the amount of current. It means when you increasing the amount of current, the amount of flux also increases. Yes or no? So suppose by very less amount of current, say 1 ampere, there is a magnetic flux is this. Agree? This is for 1 ampere. Okay. Now, if you increase the voltage, so simultaneously current will increase and here flux will be increases. Yes or no? Then after up to 3 ampere, when you increase the current up to 3 ampere, flux is also increases. Agree or not agree? Yes. So you can see by some proper arrangement, you can increase the amount of current. Simultaneously, your flux link with the coil also increases. This means a changing flux is there. Yes or no? Changing flux is there. Like here, the polarity is plus and minus your main applied EMF. So current is flowing in this direction. So your polarity rises is plus and minus of changing EMF. Clear? So this change in flux, yes, you know the changing flux will rise an EMF. Clear or not? The changing flux will rise an EMF. And according to the Lenz's law, the direction of EMF is opposite to the cause who created. So there is a opposite direction. In opposite direction, an EMF will produce. This EMF is called back EMF. Okay. Why the name of this EMF as back EMF? As this EMF is against to the applied EMF, which is E here, V here. Okay. Your applied battery is V, and due to the change in current, there will be a induced EMF produced opposite to the applied EMF. This is called back EMF. So you can say an EMF is produced, and this phenomenon is called self-induction because this EMF rises in the same coil where you have applied your main EMF. Okay, against of that, there is a rise of back EMF, and this process is called self-induction. Clear or not? Yes. So concept of self-induction, your applied your amount of current I, sorry, flux, your flux in the primary coil or in the same coil is directly proportional to the current I. So flux is directly proportional to the current I. As you increases the amount of flux, amount of current, your flux will be rises. Agree, beta? So phi is proportional to I. So phi is equals to Li. L is a constant here. That is the property of a coil, given coil is called coefficient of self-inductance. coefficient of self-inductance or sorry, coefficient of induction or self-inductance of a coil. Clear? Self-inductance of a coil. Clear, beta? So phi is equals to Li. We got phi is equals to Li. Now, amount of induced EMF. Let's find the amount of induced EMF. As we know, A is equals to minus of d phi by dt. Okay, agree. So place here the value of phi minus of d by dt, and here the value of phi equals to Li. Clear? As L is a constant, so you can take it out. L di by dt. This is what? This is self-induced EMF. Previously, it was only induced EMF, but now this induce is carried out by changing the current in the same coil. So this EMF now is called what? It is called self-induced EMF, right? Yes. So it's moving with the proper theory. What is self-induction? So self-induction, it is the property of a coil by virtue of which the coil opposes any change in the strength of current flowing through it by inducing an EMF in itself. Yeah. When there is a coil and a changing amount of current is flowing through it, okay, changing amount of current is flowing through it by giving some proper amount of changing voltage plus and minus here, definitely there will be a changing current. So changing current will rise a changing flux, and changing flux will rise a EMF that will be in the opposite nature of the changing current. Yes or no? Yes, this is called back EMF, or this is called self-induced EMF. So it is a property of a coil by virtue of which coil poses any change in the strength of current flowing through it by inducing an EMF in itself. Okay. And this EMF is called self-induced EMF. When current I is increasing, yes, see here, the current is growing. When the current is increasing, the self-induced EMF appears across the coil in a direction such that it opposes the increase. Yes, when current is rising, the EMF will be produced in such a way that it opposes the rise in current. Means it is in opposite direction. Understood? So how do it oppose? Like your growing current supporting the polarity of plus to minus, as current is going in the same direction plus to minus, right or wrong? Then your induced EMF, your induced current, your induced EMF having a polarity of plus here and minus to oppose this increasing current. Clear or not? Okay. So your source polarity is plus 2 minus. Then your induced EMF polarity is in the same. For the plus terminal, it will be at minus, and for minus, it is equal to plus. Means opposite polarity. Clear? So when current I is increasing, the self-induced EMF appears across the coil in directions such that it opposes the increase of main current. Therefore, it would be in a direction opposite to I. Second case, now your current is decreasing. Your current is decreasing. Okay, in the first case, your current is increases from 0 to 5 ampere when you switch on the circuit. Now, when you switch off the circuit, it means current is decreasing from 5 ampere to 0 ampere. Okay, so the induced EMF will produce in such a way that it will support your current. Okay, support your current, not to decrease the current. Yes, so it will be in the same direction. Understood? It will oppose the decreasing of current. So it will give a backup to your current and produce an EMF in the same direction. Okay, to support it. Because induced EMF does not like changes. Okay. If you increase, then it will in your opposition. And when the current will decrease, it will opposite. The nature is opposite of decreasing. Clear? The induced EMF is against to decrease of current, so it will support your current. Yes, so when current I is decreasing, the self-induced EMF appears across the coil in a direction such that it opposes the decrease. Yeah, the direction of EMF will opposes the decrease. Means it will support your current. Okay, therefore it would be in the direction of I. If your current is increasing, then the polarity will be in opposite direction and EMF will be in against. When your current is decreasing, your EMF is in support. Right? Clear? Yes. Self-inductance. Now this is process of self-induction. Now self-inductance. What is self-inductance? Self-inductance is a physical quantity or property of a coil. Let the current I is flowing through a coil at any time, and phi is the amount of magnetic flux linked with all the turns in the coil at that time. Then it is found that phi is proportional to I. Yes. So phi is equals to Li. Okay. L is here constant of proportionality and it is called self-inductance or coefficient of self-induction of the coil. The value of L depends on the number of turns, area of cross section and nature of the material. Yes, we are going to derive this relation, that is very important. So in that we will see the value of L is depending on the number of turns. Okay, number of turns, area of cross section, nature of material means mu, nature of the material of the core on which the core coil is wounded. All the things will be evident from the derivation. We are going shortly, we are going to derive that. Clear? Mm. Now, to define coefficient of self-induction or self-inductance, check here. Phi is proportional to I. So, phi is equals to Li. So, what is L is equals to phi upon I, right? So, to define L, coefficient of self-induction or self-inductance, how can you define? If I is equals to 1 ampere, consider I equals to 1 ampere. Yes, there is a coil and amount of current you flowing is equals to 1 ampere. Clear? So place the value of I is equals to 1 ampere, then L equals to what? Phi. Means when a flowing amount of current is 1 ampere, the amount of flux is linked with that coil is called is equal to is self-inductance. Yes. So if I equals to 1, if I equals to 1, phi equals to L into 1 or L equal to phi, means self-inductance of a coil is numerically equal to the amount of magnetic flux linked with the coil when unit current flows through the coil. Yes, when unit current is flowing through any coil, that time amount of flux linked with that coil is equal to, numerically equal to self-inductance, coefficient of self-inductance. Clear? Means higher will be the self-induction inductance of the coil, higher will be the amount of flux linked with the coil. Clear or not? Sure. See, we have the formula phi is proportional to I. So phi equals to Li. Now L equals to phi upon I. Yes or no? Phi upon I means amount of flux per unit current. Amount of flux per unit current. Unit current. Okay. Now, if I equals to 1 ampere, when you have provided current equals to 1 ampere, now place the value L equals to phi divided by 1. So, L equals to phi, right? So, self-inductance is numerically equal to amount of flux linked with that coil. Clear or not clear? So, what is self-inductance of a coil is numerically equal to the amount of magnetic flux linked with the coil when unit current flows through the coil. Clear? Yes. One more definition. The EMF induced in the coil. Yes, I already derived this one as E equals to minus of d phi by dt. And by the formula of self-inductance, phi is equals to Li. So L can be taken carried out as it is constant. So E is equals to minus L di by dt. Beta, basic two formulas are there in the self-induction. First, it is phi is equals to Li. Yes, note it. Phi is equals to Li. And second, it is induced EMF E equals to minus L di by dt. Clear? Yes, E. E equals to minus L di by dt. Minus L di by dt. Right? Now, the unit of SI unit of L is Henry. The SI unit of L is Henry. Clear? Now, one more thing. Yes. E is equals to minus L di by dt. Yes, we can derive one more definition of L. How? See. So we have the formula E is equals to numerical EMF equals to L di by dt. Yes. Minus sign, if you minus sign, then this means the induced EMF will opposes the change in current. So L is equals to E upon di by dt. Okay. Yes, L equals to E upon di by dt. If di by dt is equals to what? 1 ampere per second. Yes. If di by dt means change of current, rate of change of current in the primary coil is equals to 1 ampere per second, then L equals to E upon 1. This means L equals to E. Now, what is definition? The self-inductance, the coefficient of self-inductance or self-inductance of a coil is numerically equal to the EMF induced upon the coil. That is, it is equal to induced EMF upon the coil when a change of current per second, the change of current with time is equals to 1 ampere per second. Okay. In another words, you can say when there is a changing current with 1 ampere per second is flowing through a coil, then the amount of EMF induced upon the coil is numerically equal to its self-inductance. Here, flowing through coil, when a current of amount 1 ampere per second is changing through coil. Okay, yes, there is a changing current. Definitely there will be a flow of current, but there is a changing current. Okay, if a current of amount 1 ampere per second, changing current is flowing through that coil, then the EMF produces on the coil is equals to its self-inductance. Clear? In simple words, you can also write when there is a current changing with a rate of when there is a current changing with a rate of 1 ampere per second. Okay, per second. 1 ampere per second. When there is a current that is changing with the rate of 1 ampere per second flowing through the coil, then the amount of EMF induced in the coil is numerically equal to self-inductance. Then the amount of EMF induced is numerically equal to the self-inductance. Student, you are trying to learn this definition, but it is quite simple. You go through the formula. Actually, what we have the formula? E equals to L di by dt. See, Nitin, here. We have the formula L equals to di by dt. Okay. So what is di by dt? It is the rate of change of current. If the rate of, this is the rate of change of current, right? So when the rate of change of current in the coil is I means 1 ampere, the unit of current is ampere, and at the denominator it is T, so it is equals to second. So when there is a change of current is by 1 ampere per second, so E equals to L into 1, so E equals to L. Okay, or you can write L equals to E. So what is your self-inductance of a coil? So self-inductance is defined as the EMF induced on the coil. But when, my dear, when the current flowing through the coil is changing with the rate of 1 ampere per second. Understood? Yes. That time the amount of EMF produced is equals to uh, that time amount of EMF is produced is equal to self-inductance. Yes. Now define 1 Henry. Next question is 1 Henry. Okay. Unit of L is Henry. Now define what is 1 Henry. As we have phi equals to Li, yes, all the definitions are derived from the formula only. So L equals to phi upon I. Yes. We have to make 1 Henry, means magnitude this one equals to 1. So what we have to take, phi is equals to 1 Weber and I is equals to 1 ampere, right? So if phi is equals to 1 Weber and I equals to 1 ampere, then the ratio equals to 1 ratio 1 is equals to 1 Henry. Clear? Now make the definition. So first you have a coil. There is a current of 1 ampere. And by flowing a amount of current 1 ampere, there is a flux linked with the coil is of amount 1 Weber. Yes, so this is the definition of 1 Henry. If by flowing a current of 1 ampere, the flux linked with a coil is equals to 1 Weber, then the inductance, self-inductance of coil is said to be 1 Henry. Clear? By flowing 1 ampere current, the flux link with the coil is equals to 1 Weber, then the amount of self-inductance is said to be 1 Henry. Clear? Yes. Next, one more definition by second EMF formula. E is equals to L di by dt. Yes, check. L equals to E upon di by dt. Right, beta? This will be L. So L will result E upon di by dt. Now, yes, this is a coil, my dear. And this is current. Yes, current, changing current, I with respect to T. Changing current means I depending on time. Yes, see here. If you changing the amount of current with 1 ampere per second, if there is a changing current in the coil is 1 ampere per second, resulting in EMF of, resulting in back EMF of 1 volt. 1 volt. Okay. By flowing a changing current with a rate of 1 ampere per second, the induced EMF is equals to 1 volt. Then the inductance, self-inductance of the coil is said to be 1 Henry. Okay. Clear? If the numerator will be 1, the denominator will be 1, then your answer will be equals to 1. Now, come to the definition. The SI unit of L is Henry. L equals to E upon di by dt. So 1 Henry, when 1 Henry will develop, when you flow the amount of current 1 ampere per second will rise as an EMF, induced EMF of 1 volt. Then your inductance of the coil will be equals to 1 Henry. The self-inductance of a coil is said to be 1 Henry when a current changes at a rate of 1 ampere per second through the coil induces an EMF of 1 volt in the coil. Right? So in this situation, your inductance is said to be 1 Henry. Clear? Okay, students, let us see a question here. Current in a circuit falls steadily from 2 ampere to 0 ampere in 10 millisecond. Okay, so 2 ampere to 0 ampere in 10 millisecond. If average EMF is equals to 200 volt is induced, calculate the self-inductance of the circuit. Okay, so we have to calculate what? We have to calculate L. Clear, students? We have to calculate the self-inductance of the circuit. This means we have to calculate L. Now, what we have the formula? E is equals to negative of L di by dt. We have this one formula, E is equals to minus of L di by dt. Yes or no? We have the formula E is equals to L di by dt. For your convention, you can write it E is equals to di means delta I and dt means delta t. Okay. So it has been given here. What is the amount of EMF produces here? This is equals to 200 volt. Okay, so 200 volt is the voltage. L we have to find. Now change in current upon change in time. So current is initially 0 ampere and it is changes, current is initially 2 ampere and it is falls to 0 ampere. So change equals to final minus initial. So finally it was 0 ampere and initial it was 2 ampere, right? As the current is changing, current is there 2 ampere and it is falls to 0 ampere. Okay. And time taken, how much? it is 10 millisecond. So right here, 10 millisecond means 10 into 10 to the power minus 3. Why 1 milli equals to 10 to the power minus 3, right? So 200 minus equals to minus L, 0 upon minus 2, so it will become minus 2, and 10 power 1 and 10 power minus 3 become 10 to the power minus 2. Clear or not? Now L minus minus and minus become cancel. Now L equals to 200 multiplied by 200 multiplied by 10 to the power minus 2 divided by 2, right? 2n cancelled out. This is equals to 100. So 100 you can write 10 to the power 2 and it is 10 to the power minus 2. Cancel each other. Answer L equals to 1. What is the unit? Henry. So inductance of the coil equals to 1 Henry. Got it? Yes. Okay, guys. So our next topic is energy is stored by inductor. Energy is stored by inductor. See the situation. We have a DC source is there. We have connected this DC source with a coil. This is the coil. And we have connected this one coil with a battery of some voltage. Okay. So when the current will start, so it will moving like this. Initially, it will have zero value. And finally, the current having its maximum value, the maximum value circuit can flow is equals to I naught. So finally, the current will attains its maximum value up to I naught, and then it will be constant like this, right? Now, up to here, the current will changing from its 0 to hero level or minimum value to maximum value. So there will be a opposite EMF continuously. Opposite EMF will produce. Okay, that to oppose the amount of current. Okay, but this battery will do useful work and finally establish the amount of maximum current I naught, okay, from the coil. So this battery has done some useful work to establish the amount of current I naught through this circuit. Understood? This battery have done some useful work to counter this back EMF that is applied by the coil and to set this current to its maximum value. Yes or no? So we have to find the amount of work done to to establish the maximum value of current 0 to I0. Clear? Yes. See here. So the question may be asked like this. A source of EMF E is used to establish the current I through a coil of self-inductance L. Show that the work done by the source of build up this current I is equals to half Li square. Okay, student, I would suggest you take I naught is the maximum amount of current to avoid your confusion. So the energy established equals to half L I naught square. I naught is the maximum value of current you set up in the coil. Okay. Okay, let us start with a consideration. The source of EMF E is establishes a current in the coil in opposition of induced EMF. Yes, there will be opposition of uh, induced current. Surely, by the Lenz's law, there will be a induced EMF. That is obviously a back EMF will oppose your uh, applied EMF and also induced current, rising of induced current. Okay, Lenz's law, and hence work is done for the same. This work done by the sources is stored in the form of magnetic energy in the coil. Yes, this battery is doing useful work to establish the current to its maximum value I naught. Okay, and this work is stored inside the coil in the form of magnetic energy. Yes, inside the coil. We have to find how much amount of work is done by the source, and that is exactly equal to the amount of energy stored by this inductor. Let I current is flows through the coil of self-inductance L. at any instant t when the rate of change of current in the coil is equals to di by dt. Okay. So suppose there is a random current, variable current I. We have started with the amount of current I. Okay. Suppose there is a current I that is continuously changing and it's a start with the amount 0 and it will grow up to the maximum current I naught. Yes, we have to find the energy stored during this process. So let I is the current flows through the coil of self-inductance L is here. Yes, the coil having self-inductance L. At any instant, the rate of change of current is equals to di by dt. So the EMF, back EMF produces by the coil equals to L di by dt. Any problem till here? Yes. Now, work done in establishing the current in the small time interval dt. Yeah. Yes. So this current has established this battery has established the current here. So what is the work done to uh, establish a amount of current I? The current I flows through the coil of self-inductance L at any instant of time t when the rate of change of current is equals to di by dt. So induced EMF equals to di by dt. Work done to establishing this current in a small interval dt is given by how? Check. You know P is equals to dw by dt. Agree? Power is equals to rate of change of work. Clear or not clear? Okay. So here dw is equals to what? Power into time. Power into dt. Clear or not? Power into dt. Now dw is equals to power equals to voltage into current. This is instantaneous power. Power is equals to voltage into current. This is formula from class 10th. P equals to VI. Okay. So applied voltage is here what? Here in the place of V, the working component is E of EMF E. Okay, in the place of V here it is working E. And that time the current is equals to I, EI dt. Right? Yes, this is the small work EI dt. Now, place the value of EMF. You know the EMF is equals to this EMF is equals to the induced EMF equals to L di by dt. As these circuits, as uh, the combination is in parallel combination, so E is equals to L di by dt. Here what? Here equals to L di by dt amount wise. So same amount of voltage will be here. So place the value of dw is equals to what is value of E? Equals to L di upon dt. This is the value of E. Got it? Into I into dt. Now dt and dt cancelled out. So this is equals to dw is equals to L I di. Right? Yes. This is equals to dw. So this is a small work to establish the amount of current I. Now we are interested to find the total work. So total work is given by integration of dw. The total work is given by integration of dw. So because continuous type of work is there, there is not discrete work like first we have done in first hour, then after some break is there, then after some, like as current is establishing in continuous manner. You see this graph, there is point to point, point to point, point to point rising of current. Yes or no? There is no any break, right? So when there is no any break, your work is you're doing flawless work, continuous work, then there will be integration. Okay. And when you're doing discrete work, then there will be summation. So these two things are there, difference, summation and integration. Got it? So this is equals to dw. Now dw, place the value here, is equals to L I di. Okay. So now check the graph. From the graph, the current rises from a lower value 0, its initial value equal to 0 and final value equal to I naught. Yes or no? So the limit will be limit of current equals to 0 to I naught. Okay. Yes, I am solving here. So dw, integration of dw, work is given by dw. So work is equals to, what is dw? Equals to L I di. Okay, and current is growing from its minimum value 0 to maximum value I naught. Okay, so w equals to, L is the constant, that is property of inductor. 0 to I0, it will become I di. Okay. Now, formula x to the power n dx for integration, this is equals to x to the power n plus 1 upon n plus 1. So here the power of I is invisible. This is equals to 1. Surely, when there is no power, this means it is equals to power 1. Yes or no? Yes. We have to place the formula, the values into the formula. X to the power n plus 1 upon n plus 1. Clear? Okay. So W equals to L. But in the place of X, I is playing here. So I to the power, existing power is 1. By the formula, power is 1 upon same result in the denominator, 1 plus 1. Clear or not clear? Got it? I to the power 1 plus 1 upon 1 plus 1. Now standard limit 0 to I0. Clear? So W is equals to L I to the power 2 upon 2. Yes, and limit, lower limit is 0, upper limit is I naught. Clear? Now 2 is a constant, so you can take it out. Only the variable part I square will be inside the bracket. Apply the limit 0 to I0. Clear? So L by 2, apply the maximum value equals to I naught square and minimum value equal to 0 square. So beta it will be equals to half L I naught square. This is the stored energy by the inductor. Clear? Yes, half L I naught square. As we have taken the maximum current is equals to I naught, so we have to put here L I naught square. Clear? Yes. Note it. So from where we have started, first we have taken the formula E is equals to induced EMF equals to E equals to minus L di by dt. This is induced EMF by some produce because of some flow of current, capital I, changing current. Now power, instantaneous power is equals to dw by dt. So dw equals to power into dt. Now P equals to instantaneous power equals to P equal to E into I. The value of E equals to L di by dt into I dt. Dt cancelled, and the small work done is equals to L di. Now the total work done can be figured out by integration of dw small work done, that is going limit 0 to I naught L di L I di. Clear? Clear? Okay, students. So make the next heading self-induction of a solenoid. Clear? Self-induction of a solenoid. So we are going to calculate on what factors the self-inductance induction depends. And if we have a coil, like we have a coil of length capital L and total number of turns capital N. Okay, total number of turns equals to capital N. Then what is the, okay, we have to change here, as L, capital L, we have reserved for self induction, so we have to take the length of the coil equals to L. Okay, length of the coil equals to a small L. Clear? So L length will contain N turns. So unit length will contain N by L. So this is equals to small n. Small n equals to N upon L, means number of turns in unit length. Understood? Yes, this is equals to small n. Now we have to derive the value of capital L. Okay, what is self-inductance of this coil? Yes, The total coil having total number of turns equals to capital N. Yes. So derive. See, consider a solenoid having capital N turns. Yes, the coil is there. This coil having capital N turns, okay, with the length L, and cross section area of the coil is equals to A. What is cross section area of the coil? This cross section having an area A, okay. I is the current flowing through it. So there will be a magnetic field given point in the solenoid represented by B. Yes, there is current flowing through this one coil, like I am making some larger coil, and a current is there, a current I is flowing there. So definitely this is like a solenoid. All you know, when a current is flowing, there is a parallel uniform magnetic field inside the solenoid, and the amount of this magnetic field equals to B equals to mu naught Ni. We have derived this one magnetic field in last chapter, magnetic effect of current, okay. So B equals to mu naught Ni. A parallel magnetic field is there. Okay, agree. So when a parallel magnetic field is there, so the magnetic flux per turn. Yes. What is magnetic flux by 1 turn? So you know phi is equals to B into A, right? B into A cos theta. Okay. So see here, phi is equals to B into A. This is phi what? This is phi per turn for 1 turn. Okay. Phi is equals to B into A cos theta. What is B? B equals to mu naught Ni. Yes, this is the magnetic field by 1 turn of the solenoid. Clear or not clear? B equals to mu naught Ni, magnetic field inside the solenoid coil. A is the area of coil, that is equals to A, and cos theta is equals to cos 0 degree. Why? You see the magnetic field is here and the coils are like this, so area will be in also same direction. So this is equals to cos 0 degree. It will give you 1. Agree? So B equals to mu naught Nia. Clear? Sorry. It is phi. Why I have written here? Yes, this was phi. This is phi per turn. Clear or not clear? No. B is equals to mu naught Ni. B equals to mu naught Ni. But now we are talking about phi. Yes, phi equals to mu naught Ni. Wait, give some time. You will understand. So this is equals to phi per turn. Okay, clear or not clear? Now place the value of small n. As you know, in solenoid, small n equals to capital N by L. So phi per turn equals to mu naught capital N upon L Ia. Agree? Because in the place of small n, you have inserted N by L, right? As the coil having is a capital N number of turns. Yes, see, the total number of turns in the coil is N. And 1 turn carrying this flux. So the total flux, magnetic flux from capital N turns. Okay, beta? What will be the total flux? The total flux is equals to 1 turn flux into total number of turn, that is equals to n. 1 turn flux is equals to mu naught capital Nia upon L. Agree? So net flux phi net total flux is equals to mu naught n square Ia upon L. L should be small because length of the conductor is taken as a small L. Okay. Again, again I have done mistake here. In a small n equals to capital N by L. Yes. Any problem? Yes. Total flux from n turns. We have calculated here. This is the flux from 1 turn per turn and total flux from n turn because total solenoid containing n turns. Okay. No, nothing is total flux from n turns. Okay. So this is equals to mu naught n square Ia upon a small l. Remember, this is equals to a small l. Okay. Yes, total length of coil. So now this is equation number one. Give it equation number one. By definition of induction. What we have read in self-induction, phi is equals to Li, right? Phi is equals to Li. Give it equation number two. So by the definition of self-induction, phi is equals to Li, and definition number one, phi is equals to mu naught n square Ia. So comparing the left part of the equation 1 and 2, so you can write by first and second, Li, capital L means coefficient of self-induction. Flux are equal both the times. So Li equals to mu naught n square, make it A before then I. So A I upon a small l, right? Now I and I get cancelled out, and this is your formula. Now you can check L mu naught n square A upon L. A upon L. So this is your capital L derived. Done? No. So this is your capital L. If you want to derive this formula in the terms of number of n small n, then what is the formula? N equals to capital N by L. So n equals to small nl. Now place here L equals to mu naught small nl whole square in the place of capital N, area divided by length of the conductor. So L equal to mu naught n square L square A upon L. One L, each of the L will be cancelled, and L equals to mu naught n square small l A. Clear? So this is the another derivation. Okay. So you will get the same definition here, mu naught n square upon L. Wait. Mu naught n square, mu naught ni. Yes. Sprint is here. Okay. Here it should be A, but area is missing. Okay. So this is not correct. Okay. Area should be there, right? Yes, so this is the correct definition for coefficient of self-induction. Now you see, but more important derivation is this one. Okay, the question is asked in this one formula. Now you check coefficient of self-induction depends on what things. First, permittivity of the core, permeability of the core. Matlab it is depending on the type of material you using. Okay. So see, here I have given an introduction about related to the material. The value of L depends on the first number of turns. Check here in the derivation. The value of L depend on the number of turns. Clear? L is proportional to N square. Clear this thing? L is proportional to N square. Second, area of cross section. Yes, it is depending on A. L is proportional to A. Right? Third, and the nature of the material, yes, it is depending on the nature of the material. Yes, this is mu naught. So L is proportional to mu. Okay, depending on the material from what the core is made up of. Done? Yes, it is inversely proportional to a small l. Yes, length of the conductor. Okay, length of the coil. Greater will be the length of the coil, less will be the coefficient of self-induction. Clear?